Hello, yo. So, just finished talking about related rates. Actually, I just filmed that as of right now. Uh, for you, though, there's my marker. I wonder where that came from. For you, this video will probably be out a day or a couple days later than that one. I thought we'd talk about L'Hopital's rule. L'Hopital's rule is very, very valuable. I know I say this a lot, and I have since we've been talking about derivatives, but L'Hopital's rule is truly probably one of the most powerful things we can do with derivatives to help us in math, higher mathematics. A lot of really complicated and impactful proofs use L'Hopital's rule, and really, it's going to help us deal with limits a lot easier, right? So let's begin. This is the no-no box, because I have the light on, it's dark outside. I have to remind myself, don't draw in there, you guys can't see what's in there. So that's the no-no box. This is an Amazon box. Anyways, let's continue. L'Hopital's rule. L'Hopital's rule is going to help us deal with limits that output indeterminate forms. Sometimes we have a limit like this, and I'm going to write it out as I talk. And this limit's going to output an indeterminate form, and we're going to go over what a couple of the indeterminate forms are now. So if you were to plug in x is equal to 0, or as x approaches 0, to this function you will get 0 over 0, which is probably the most common indeterminate form. Happens in fractions a lot. Usually it's because you have a hole in your function, and most of the time you can just factor out some term, cancel stuff, numerator, denominator, simplify your function, and then be able to take a limit, kind of converging on that point, and get an output that isn't an indeterminate form. Now, other indeterminate forms, we have infinity over infinity. It's another one you'll get. I know, correct me if I'm wrong, but I believe infinity minus infinity is also one. This is in a L'Hopital's rule indeterminate form. With L'Hopital's rule, we're only worrying about fractions. So we have kind of things in the numerator and denominator that are going to output us these two here. Now, there are a couple other indeterminate forms, like 0 to the 0th power, I think infinity to the 0th power, I think infinity to the infinitieth. No, I forget. Forget all my indeterminate forms. These are the ones that matter, though. These are the two that matter the most. So, what is L'Hopital's rule? Let's go through a hard definition, as always, and then we're going to kind of take a look at how I like to think about it, go over some more kind of textbook stuff. In case you're in a calculus class right now, specifically like AP, right? I know they like to talk about writing a lot. L'Hopital's rule states that given some limit as x approaches a, is going to give you indeterminate form. That's going to be 0 over 0 or infinity over infinity, because it has to be a fraction. We're going about fractions only if L'Hopital's rule, right? So given this, the limit as x approaches a of, and then I'm going to write kind of numerator and denominator here as functions, right? Kind of how if this top was f of x equals sine of 2x, g of x is equal to sine of x, right? So this limit here, as x approaches a, of f of x over g of x is equal to the limit as x approaches a, same input, very important, of f prime of x over g prime of x. Now, your eyes are not deceiving you. It is really that easy. You just take the derivative of the top, and you take the derivative of the bottom, poof, you don't have an indeterminate form anymore, most of the time. Cool. I'm gonna write this big, bold, and red. No quotient rule. Yay, right? We don't have to use the quotient rule. Sometimes the quotient rule can get big and messy, and we don't like to use the quotient rule when we don't have to. L'Hopital's rule, we literally just take the derivative of the top and the bottom, totally independently with respect to the same variable. It's going to be that input x. I always like to think of it d top, d bottom. I don't know if that's going to help anybody, but the big takeaway is that it's not quotient rule. You are not taking the derivative of the entire fraction you're taking the derivative of the top and the bottom, right? Please make that clear. Do not make a mistake. It is not the same thing to take a derivative of the whole fraction. It is not the same thing. Now, other key takeaway is that your input stays the same. X approaches A, does not change. So you're taking these derivatives, but the input does not change. You don't have to do any kind of substitution. You don't have to solve for a new input value. It just stays, right? And so now we're going to go through some examples. And then we'll talk about some writing, and then we'll probably be done. So we can go back over to this top limit here. I'm going to erase this so we have more space. And keep the no quotient rule up there because that's important. This right here is going to equal the limit as x approaches 0. Okay, now let's take the derivative of the top here, sine of 2x. Now the derivative of sine is cosine. Remember from our trig derivatives, cosine of 2x. But we have this chain rule here, because there is not just x, just jammed my leg on that, not just x inside of that kind of those parentheses. We're not taking the cosine of just x, we're taking the cosine of 2x. So we're going to multiply that by 2. The derivative of that chain, 2x, is 2. Now all that divided by simply cosine of x, because the derivative of sine is cosine. And now, if we plug in this limit, we get, now we can remove this limit notation because I'm plugging in 0. We get 2 times cosine of 0 over cosine of 0, which is equal to 2, because cosine of 0 is 1. Doesn't matter if you're talking about degrees or radians. Mostly talking about radians most of the time here in calculus land. But that's going to be equal to 2. So, marvelous thing how we turn this limit, which normally would output an indeterminate form, into one that outputs 2. And if you were to look at the graph of this function, right, you can actually do some weird trig substitution stuff. You don't have to use L'Hopital's rule, but L'Hopital's rule is going to be the easiest way to solve this limit. If you look at the graph of this function I have here, it's actually just a cosine graph with a hole at x equals 0, and that's at y equals 2, right? So that's an interesting thing. You can graph kind of this original function, and it's going to output same thing here, right? Now, one thing I did kind of forget to do, because it's one thing I wanted to introduce next, is the unique notation for L'Hopital's rule. It's always preferred that whenever you are applying L'Hopital's rule, kind of write little LH above your equal sign. Seems kind of weird to don't do that in math ever, but it's important here because sometimes when reading a big block of math, if you're grading something or looking at a proof, really, really confusing when you just see this limit turn into this limit, especially when it gets a lot more complicated and you have no idea what's going on, right? So be kind. If you're graded on this, you'll have to put LH above there. Just indicates to whoever's reading this, we are using L'Hopital's rule. Now I'm going to go down kind of here. We're going to do another example, a quick one. I'll just kind of go through a very common function, sine of x over x. You've probably seen this one a million times graphically. It looks like, let's see, I have a hole here. Kind of has some oscillatory motion. It's going to be nice bounded oscillation. Wait. I haven't talked about the types of oscillation. Maybe we did in one of the very first videos. It's going to be type of oscillation here. Yeah, you're approaching 0 as your x tends towards infinity, right? You don't just keep going back and forth forever. Now, if I think we've also tackled this function before in a past video because it's a very common one. This hole is at y equals 1, x equals 0. So we already know this is going to equal 1. But if we just normally evaluate this limit, we get 0 over 0. So I'm going to go ahead and use L'Hopital's rule. Turn this into the limit as x approaches 0 of cosine of x over 1, which is just equal to 1. And that's another way you can get this limit. You don't have to look at a graph of the function. You don't have to kind of you do any like left hand limit, right hand limit stuff, think about what's happening on your function. You don't have to do any plugging in near values as you would sometimes in very tough limits. You can just use L'Hopital's rule, and it's very, very quick, simple. Now, if all you're here for is to learn about L'Hopital's rule, that's really all I have for new stuff. I'm going to talk about writing now, just kind of more formal stuff in case you're in a class. So I like to make sure that all audiences are included. Goodbye if you're leaving now, though. So, formally, when you're addressing L'Hopital's rule, you want to justify your use, right? Especially if you're being graded on writing. You're always going to want to say, and it's going to kind of go back up to this textbook definition here, where derivative of top, derivative of bottom, all that stuff. You're going to write, go ahead, since the limit as x approaches a of f of x is equal to 0. Now, if you think we're only dealing with fractions here, we can split up kind of this limit into the limit as x approaches a of f of x equals 0 and the limit as x approaches a of g of x equals 0. Now, by saying this, you're implying that, you have a function here in this limit as x approaches a of f of x over g of x. By reading this, your reader will understand, okay, this is going to output an indeterminate form, because remember, in formal mathematics, you cannot simply write that something equals 0 over 0 or equals infinity over infinity. You're not allowed to do that strictly. However, you can say that because this numerator is going to be equal to 0, and because this denominator is going to be equal to 0, I can apply L'Hopital's rule. That's what I'm going to write here. And then I'm going to write LH by L'Hopital's rule. And then we're going to kind of restate our limit. The limit as x approaches a of f of x, and this kind of restates it, and then over g of x, kind of tying this top reasoning, this because this, then this. And then we're going to go ahead and write LH. Remember, that's another formal thing we have to do. Indicate that we're using, that we are applying L'Hopital's rule through this transformation here, right? Equals the limit as x approaches a of f prime of x over g prime of x. And this is a formal way to indicate you are using L'Hopital's rule, since the limit as x approaches a of f of x is equal to 0, and the limit as x approaches a of g of x is equal to 0. By L'Hopital's rule, the limit of f of x over g of x is equal to the L'Hopital, L'Hopital transformed limit as x approaches a of f prime of x over g prime of x, right? So, and this works with infinity too, because infinity over infinity is another common indeterminate form. Not really until we start dealing with exponential functions, logarithmic functions. We haven't got there yet. Okay. And so, another thing that's going to come up more later, and we might not have another video over L'Hopital's rule once we cover functions like e to the x, other exponentials, and logarithmic derivatives. We're probably going to leave L'Hopital's rule here as is now, but we can apply L'Hopital's rule multiple times. So let's say f of x is twice differentiable, meaning simply that f double prime of x exists. Really, if f is differentiable, it's because your derivative exists. Right? If your derivative didn't exist, it would be differentiable. Because differentiable continues, right? If double prime exists, g double prime exists. You can go further. The limit as x approaches a of f of x over g of x is going to be equal to, and then you can, our limit notation is equal to limit as x approaches a f prime of x over g prime of x, right? This is our normal L'Hopital's rule. However, if this still outputs an indeterminate form, because that is possible, especially with higher degree functions, exponential functions, logarithmic functions, you can keep going. You can take another derivative of the top, take another derivative of the bottom, and follow the exact same process, change absolutely nothing until you get it. Because eventually, with L'Hopital's rule, you will one day get it. You will always, as long as the function, I mean, the only thing I can guess wouldn't work is if you had some like weird, goofy function that like has an area which it doesn't exist, and you're trying to find some limit of in this area, and you just keep taking derivatives forever. But then you'd start to notice some trend of kind of expanding derivatives. Um, and there's probably something you can do with like infinite series and like further down the line calculus stuff that we'll talk about later. But for calculus 1, 2, you'll never have to worry about using L'Hopital's rule forever. I've only had to use it like 3 times at most, maybe for like super higher order degree function that some person at some university or research institute really wanted to test to make sure you know how to use L'Hopital's rule. They made a question very long in that. Must be very evil people. It must be. Totally can't be good. But anyways, it's L'Hopital's rule. Very useful trick. I hope you look back on limits we've done in the past and you scream at me for not teaching you this earlier, because this is incredibly useful for dealing with tricky limits. So see you later, class. See you in the next one.